A disc and hoop of the same mass and radius are released at the same time at the top of an inclined plane. If both are uniform, which one reaches the bottom of the incline first? If there is no slipping. Okay.
I think I put C. I thought they were gonna be the same, but
Yeah.
but it's
Okay,
the disc. Does it just depend on like the shape of it or like how it rolls or
Yeah,
something?
it does depend on the shape. So what I would do is I would look at like, so you have like a hill, you have your hoop, and then your like disc, right? And it's in
Yeah.
a spot, you let them go. So I would look at basically whichever one has like a faster velocity is gonna get down to the bottom
Yeah.
first, right?
Yeah.
So what I would do.
But if they're the same mass and radius, that's why I figured they'd be the same.
Yeah, yeah.
Since they're the same, but.
Right, so this is kind of the same idea as last time, right? So we have our
Yeah.
total kinetic energy. It's gonna equal our like translational plus rotational.
Yeah, the potential energy up there at the top, right?
Yeah, well, yeah.
I see
No,
what
yeah,
you're
that's
saying
right.
now.
Right, yeah. So potential energy equals this.
I see what you're saying.
Yeah, so this would really be at the bottom.
Yeah.
But like anywhere it's moving, it has potential and kinetic.
Yeah.
And the kinetic is both of those.
Yeah.
So we got our 1/2 mv squared, and then our 1/2 moment of inertia, that squared, right? So we're just gonna kind of do the same thing we did before. So our I, let's just do for the thin hoop first.
Do they have different formulas like a disc and a hoop?
Mm-hmm. Well,
Or-
not for this. This is for both.
Yeah.
But the hoop has so the hoop's moment of inertia is mr squared, and the disc, its moment of inertia is 1/2 mr squared. So they have different moments of inertia.
So that's what, the moment of inertia is what determines.
Yeah. Well, it will affect its velocity.
Yeah. Okay.
Yeah. So if you were to plug this in, if this was like the hoop, you'd have like mr squared, your v squared over r squared, right? Cancel those guys. So you get like 1/2 mv squared plus 1/2 mv squared. So in the end, you add them together. For the hoop, it's just mass times velocity squared, right?
Okay. Yeah.
So then for the disc, we start with the same formula. And then we use our I for the disc, which is some moment of inertia. Then we do our same. So you get 1/2 mass times velocity squared plus 1/2 times 1/2 this time, so we get 1/4 mv squared. So you add them up, you get 3/4 mv squared. So this is for the disc. And this is for the hoop. So if you were to have some number here, because they're going to have the same kinetic energy at the top, at the bottom,
Yeah.
at the top. So you can have whatever number here, it doesn't matter. It's going to be the same number. When you solve for velocity, so in this case, you're just going to have velocity equals, well, we can just say velocity squared, equals like x divided by m, right?
Uh-huh.
And then this one, it's going to be 4/3 x divided by m.
And that's the
This is the disc.
disc.
Yeah. So you'll notice the disc's velocity should be higher.
Okay, yeah.
So it's going to reach the bottom first. So when you compare those two, this one, since it has since the whole thing's being multiplied by 4/3,
Okay.
it has a higher velocity than the thin hoop. So therefore, if this thing has a bigger velocity, it's going to get to the bottom first.
Okay.
Just kind of how it works. So.
Okay. Okay.
So yeah.
So if I were to do this problem to show my work, can I just plug in random numbers for the mass and radius but just make sure they're the same.
Right, yeah, you
for
could.
both of them. And,
you could do that.
And then,
Well, yeah, I really wouldn't need the radius, you just need the mass. And then some sort of potential energy.
because the radius.
Yeah,
comes
you
out.
could say X is like 50 joules or something
Okay.
of potential energy that they have, or whatever, it doesn't matter. And then you'd plot, so mass maybe is like 10 kilograms, 10 kilograms, 50, 50. When you solve it out, you'll notice this velocity is going to be higher.
Okay.
And I wouldn't, yeah. I mean, you probably don't even need to plug in numbers.
No,
you could probably
I-
just do
yeah,
this. But
yeah.
yeah, you could just
Okay.
make up numbers if you wanted.
Okay.
Yeah. Yeah, that one's kind of tricky, huh? It's kind of weird.
Yeah.
Because you see time and you're like, how the heck does time have anything to do with it? Even this is still kind of like, which one has a bigger velocity? You still have to understand this part, which is kind of confusing, like,
Yeah.
can throw you off too, so.
Yeah, the whole moment of inertia thing, I think, is just what, not because moment of inertia for both of them are different, and they depend on, and the velocity depends on the
Yeah,
moment of inertia.
Mhm.
So that's what, I think that's what messed me up.
yeah, for sure.
Why I just put both of them, because I figured same mass, same radius.
Yeah, like, what's the
Should go the
difference, right?
same if-
Yeah, it's because they have different moments of inertia. So even though they do have the same mass and radius.
Yeah.
Yeah.